Quantum chromodynamics, or QCD for short, the theory of strong nuclear force, is one of the most elegant yet frustrating theories mankind has ever produced. Can you explain what aspects of QCD makes it an exciting research field as well as a pain to work with at times?
Thank you very much for that question. Let me begin by saying that quantum chromodynamics, or QCD for short, as it noted, is the theory of interacting fundamental quark and gluon fields. For those of you who may be unfamiliar with this theory, quarks are spin 1/2 fermion fields that carry mass and fractional charge, and gluons are massless, electric charge, zero electric charge, spin 1 boson fields. So these properties are analogous to the electron matter fields and the photon force carriers of electrodynamics, which you may be more familiar with, or QED in short. However, quarks and gluons carry another charge, whimsically called color, where the chromo in chromodynamics comes from. And this dictates the strength of the interactions of quarks with gluons, and most remarkably, gluons with each other. So this is really striking because, unlike photons, gluons can self-interact. And this makes QCD a profoundly different theory from QED. And these colored self-interactions underlie all the beauty and complexity of the theory. One remarkable consequence is that gluon self-interactions lead to the anti-screening of quark color charges that are mediated by gluon exchanges. And this is in stark contrast to the screening of electron interactions. What this means is that the strength of quark and gluon interactions becomes weaker the closer they get to each other, a phenomenon that's called asymptotic freedom. When it was discovered, it was a complete surprise, because everyone thought that the strong force would get even stronger at small distances, just as would be the case in QED. So this was really took the physics world by surprise, and it led to a revolution in our thinking about the strong interaction, and immediately explained a lot of puzzling experimental results in the data that existed until then. In particular, those from so-called deeply inelastic scattering experiments that I'll return to later in our discussion. And this discovery of asymptotic freedom justly led to the Nobel Prize being awarded to David Gross, Frank Wilczek, and David Politzer, who discovered asymptotic freedom more than 50 years ago. The other profound consequence of gluon self-interactions, besides asymptotic freedom, is that quark and gluon interactions grow much stronger at larger distances. So it's the converse way of asymptotic freedom, which means that if you try and pull apart the quark and anti-quark, so at very short distances, they're weakly interacting, but as you pull them apart, it's like stretching a rubber band apart. And at distances already as large as 10 to the minus 15 meters, the rubber band snaps. So the force is so strong that the rubber band snaps, and it produces further quarks, antiquarks, and gluons from the vacuum surrounding the original quark-antiquark pair. And that ends up in producing a colorless pair of quark-antiquark objects called mesons. For a long time, people thought that quarks and gluons and color charge were just mathematical abstractions that provided a kind of taxonomy of the zoo of subatomic particles, mesons and baryons, that were being produced in experiments. So that was what the strong force looked like. It was that you had all these subatomic particles, and no one really understood fundamentally where they came from. So quarks and gluons were a way to classify these objects. They weren't, no one thought that these would be actually something real, and if they were real, one would expect to see them. So what QCD explained was this lack of observation of quarks and gluons was not a bug of the quark-gluon picture of the strong interactions, but it was a feature, a most striking property of the theory called confinement. Now, there are formal mathematical definitions of confinement but a good empirical definition is to say that the spectrum of observed states in strong interaction experiments can only be colorless objects. The existence of color charge, and indeed of quarks and gluons, can only be inferred from such measurements. Confinement is a rather pedestrian word for something truly remarkable. In my view, for the first time in the history of science or human reasoning, we arrived at a novel twist to the reductive paradigm which is that if we look deeply enough, we see the objects and the interactions that make up matter. To this, QCD says both yes and no, that indeed there are such objects, but that what we mean by C is more complex. Now, one could argue that the no in this dichotomy is prefigured by quantum mechanics. But what QCD says further is that what we think of as the vacuum, right, the zero energy state there is a deeply complex object, which further complicates our interpretation of what we measure. So to summarize this rather long-winded answer to your question, QCD is elegant because it explains, predicts, and allows us to compute with high precision a lot of strongly interacting phenomena. The painful part is that we don't understand the dynamics of confinement fundamentally. It is the elephant in the room that limits our complete understanding of the strong force.
Thank you so much for that answer. You explained about QCD, and many people describe it as one of the most perfect theories ever known. Why do they call it so?
So one way to think about it is to think about the Lagrangian for the theory, QC Lagrangian, which gives you the equation in motion, in the limit of zero quark masses. So this limit, so that's not very realistic, but you can just, in the Lagrangian, as a theorist, you can put these quark masses to zero. So in this limit, the theory has no parameters at all. There's no parameters in theories. It has remarkable symmetries. It has a local gauge color symmetry, a global chiral or handedness symmetry of the quarks, and symmetries related to global baryon number, axial charge, and scale invariance, in addition to the discrete charge, parity, and time reversal symmetries. All these symmetries, except color, are broken by effects of the QCD vacuum and quantum effects that strongly influence the dynamics of these quark and gluon fields. And this leads to remarkable emergent phenomena, such as spontaneous chiral symmetry breaking confinement, the confinement I talked about previously. Now, when you turn on the quark masses, right, these are parameters in the QC Lagrangian, they're very important for the real world. So the real world as it exists would be very different if you had different values for these quark masses. However, their role is to modify the already rich emergent phenomena that exist even in their absence, so where QCD has no parameters at all. So that's why we like to say that QCD is the most perfect theory, because it has this enormously rich emergent structure which would exist even if the theory had no parameters at all.
That is very interesting. So let me focus on a topic in QCD, the topic of gluon saturation. What is gluon saturation? Why is it so important to discover? And where are we in terms of the experimental evidence?
Gluon saturation is one of the striking consequences of QCD. And it's observed in the interactions of strongly interacting probes with matter, so say protons and nuclei, at very small distances within these objects and at very high energies. So when these conditions are satisfied, and as you increase the energy of the probe relative to that of the proton and nucleus, what the probe sees or interacts with is a kind of Markovian type process where the change in the number of an object depends on the number of objects there previously at each step. So the growth of the COVID virus is an example of the Markovian process. And as that has taught us, this Markovian process consists of a very rapid proliferation of color charges, mostly gluons, that are seen by the probe as its energy relative to the probe increases. And so as you increase the energy of the probe, relative to the proton or nucleus, what the probe's going to see is more and more of these gluons proliferating very rapidly. And each of these gluons carries a very small fraction of the proton's momentum. Now, asymptotic freedom tells us that a probe, because it's so small, right, should interact very weakly at these distances. But the very large density of gluons that this probe interacts with compensates for this very weak interaction. And so that tells us that the probe will scatter at some high enough energy with unit probability of this very high occupancy of gluons when that occupancy reaches some critical value. Now, what happens if we increase the energy even further? So the way QCD deals with this cleverly is by screening the gluon color charge at smaller and smaller distances, so they become less visible to the probe. And this screening scale, which varies with energy, is an emergent scale of the theory. And that scale is this gluon saturation scale. And this phenomenon of screening color charge to maintain a maximal occupancy allowed by the theory is what's called gluon saturation. Now, in my view, you asked about experimental evidence. Gluon saturation is ubiquitous in collider experiments. For instance, all event generators that generate the structure of soft events in high energy collisions, in some fashion implement aspects of this physics. However, a quantitative and systematic comparison to theory is still lacking because the separation of scales between this emergent screening scale in the theory, the saturation scale, and these scales corresponding to actual confining dynamics that I talked about earlier is not as clean as we would like it to be.
So before we get into our most recent work, let me treat our viewers by talking about your past research. In a series of now classic works, you and your collaborators developed the idea of color glass condensate. Can you describe what this color glass condensate is?
Because of the aforementioned complexity of QCD, dealing primarily with confinement of quarks and gluons at larger distances, physicists often who work in the strong interactions often work with simpler so-called effective theories of QCD that accurately capture the dynamics of the theory in different kinematic regimes. So we have several such effective theories. And the CGC is the particular effective theory that describes how gluon saturation happens and allows us to compute systematically the many-body correlations of such lumps of glue at these tiny distances. The color in color glass condensate obviously refers to the charge carried by gluons and quarks. The glass is interesting because this comes from the interactions of the soft, lumpy gluon matter, and that occurs on vastly different energy scales, which is characterized by some power law behavior. These energy scales are vastly different compared to those of the harder quarks and gluons, sometimes called partons, that carry the quantum numbers of the proton, right? Like say electric charge, baryon number. So even though the hard partons have color coupling to these soft gluon lumps, this coupling, because of the very different time scales, is of a stochastic nature. And so experiments would effectively measure some averaging over these stochastic averaging over these harder parton degrees of freedom. And that is the case also with other kinds of glassy materials, that there's a separation of time scales in certain degrees of freedom, which kind of have stochastic interactions and the strongly correlated dynamics of the underlying matter. So that's where glass comes from. Now, what about condensate? The condensate is a bit simpler to understand because it just refers to the very high occupancy of gluons in this lumpy matter, color glass condensate. And the gluons with this high occupancy all have a given roughly constant, a very specific emergent momentum. And this is the case for Bose-Einstein condensates that we are familiar with. So that's where the word color glass condensate comes from.
Thank you very much. So now let me focus on your most recent work. Some of our most recent work has focused on these dualities between high energy QCD and gravity. Can you explain the connection that you drew in these seemingly different theories?
I believe you're referring to the double copy structure of certain gravitational amplitudes to those in Yang-Mills theory. Much of this work can be traced to the relations between the low energy behavior of closed and open strings. The so-called covalent tie or KL3 relations and their mathematical underpinnings. Now, sometime later, Bernd Carrasco and Johansson, often called BCJ, and the collaborators, showed that these KLT relations can be expressed as color kinematic dualities, whereby color factors in Yang-Mills amplitudes can be replaced by kinematic factors to obtain gravity amplitudes. This is now a highly developed field and recently has achieved additional prominence because of the application of these methods to compute high-order post-Minkowskian corrections to the effective Hamiltonia describing binary black hole mergers. Our focus is a little different, and so by our I mean collaborative work with Himanshu Raj. And it's on a different, but no less remarkable double copy relation that was found between Yang-Mills theory and gravitational amplitudes by the Russian physicist Lev Lopatov in 1982. And so this was even prior to the KLT work that I mentioned. So what Lopatov found was that in the so-called high energy or ray J asymptotics of QCD or Yang-Mills theory rather than gravity, that there exists a high energy double copy, which can also, we now understand, can be thought of as a classical color kinematic duality relation. Our hope is that a deeper understanding of this Lopatov double copy can provide us with deeper insight into a quantum field theory based picture of the formation of primordial black holes.
So going along the lines of your previous answer, in a recent paper with Gia Diwali, you drew some correspondence between black holes and color glass condensate. Can you explain this correspondence?
Yeah, indeed. So your previous question really was actually inspired. My work, which connected to your previous question, was inspired by this correspondence that Gia and I conjectured. So I talked earlier about the CGC as describing lumpy, overoccupied states of gluons. And because of the very high occupancy, these states can be thought of as macroscopic quantum states. Now, another feature of the CGC is that a probe that scatters of this lump scatters with unit probability. So what the CGC does is that it saturates unitarity in high energy scattering of 2 gluon states into n gluon final states. Now, if we did a naive estimate of this 2 to n scattering, one would conclude that such lumps would be exponentially suppressed. The likelihood that you could form a macroscopic classical state from the high energy scattering of these 2 gluons would seem extremely unlikely. However, in reality, we find that that is not the case because this suppression, this exponential suppression, is compensated by a very large degeneracy factor. Okay? And that corresponds, right, the exponential of this, so it's an exponential degeneracy factor, and the argument of exponent is nothing but the microstate entropy of this classical stuff. So the state has a huge microstate entropy, which actually allows such processes to occur. Now, as our previous discussion alluded to, so this was a discussion we had on the color kinematic duality and the classical color kinematic duality. So that showed us that a similar phenomenon occurs in 2 to n graviton scattering. So where you have 2 gravitons going to an n graviton final state. So this had been noted over a decade ago by Gia Diwali, who with his collaborators developed a so-called quantum portrait of black holes described as overoccupied states of such gravitons. So Gia and I realized in talking to each other that because the CGC and black holes are respectively gluon and graviton classical macroscopic quantum states that saturate unitarity, that they share universal features that can be expressed by the Goldstone dynamics of these classical lumps. In particular, we argue that they saturate the Bekenstein area law, saying that it's the maximal entropy you can contain in a certain, for objects of a certain energy in a given area, in a given volume, I should say. And we argue that this Bekenstein area law is saturated in by these two classical lumps by the corresponding emergent Goldstone scales that describe these objects. So much of the double copy work that I described to you previously is towards quantifying this conjecture by Gyardwali and myself.
So, a central work of your research is also focused on providing predictions for the upcoming EIC, or the Electron-Ion Collider. What observations that are missing in current experiments will the EIC provide, and how will it directly impact your research?
One aspect is indeed the discovery and characterization of the many-body physics of this gluon saturation phenomenon that I mentioned previously. Right now, we have only qualitative evidence for gluon saturation from the collider experiments at RHIC and the Large Hadron Collider, the LHC. This is in part because the typical final states in these collider experiments are quote-unquote messy, with multiple effects coming from different energy scales that possibly contribute to and complicate the interpretation of these states, these configurations, as being due to gluon saturation. The EIC, in contrast, because it contains a well-calibrated, I should say, electron probe, will be very clean. Further, it's a remarkably versatile machine, allowing us to vary a wide range of energies, ion species, all the way from proton to uranium nuclei, and polarizations of the hadron beams, of especially protons and light nuclei. Further, it has an extremely high luminosity, so these electron beams are very bright, and that allows us to perform a wide range of differential measurements. And I'm hopeful that the clever measurements with this range of possibilities given by the machine will help us uncover the physics of this novel regime of QCD.
Recently, QCD celebrated its 50th anniversary. Now, as the theory transitions into its golden years, where do you think major breakthroughs might happen, and what are some promising areas of research?
So I would like to think of golden years as not as just theory riding off into the sunset with its best achievements behind it, but ahead of us. As we discussed, we still don't fully understand some of the most defining features of QCD, such as chiral symmetry, breaking, and confinement. I'm hopeful that the EIC will provide us with fresh insight and surprises that we can't anticipate now. Just as Bjorken scaling observed in previous DIS experiments led directly to asymptotic freedom. As I mentioned, that revolutionized our thinking of physics and really fundamentally changed how physicists were approaching problems in the strong interactions. Such discoveries at the EIC could, again, potentially revolutionize not just our understanding of QCD, but other areas of physics. For instance, how we think about the role of emergent phenomena when we construct beyond the standard model theories. That's just one example. One of this machine, the EIC's powerful features, is that it can provide precise space-time information on the distributions of quarks and gluons and their spatial correlations as a function of energy. So I'd be curious to understand if we can develop a kind of tomography, for instance, of the gluon lumps that we discussed. Will these high resolutions achieved and the huge luminosities of the experiments allow us to develop a spatial picture of how quarks and gluons form hadrons, for instance? I'm also interested in understanding whether quantum information measures, such as entanglement entropy, mutual information, and so on, can provide novel insight and predictions into how these strongly correlated systems organize themselves.
Looking ahead, what are the primary directions for your research in the next 5 years? Are there some specific questions that you would like to answer?
So one area I would like to pursue is, as was probably clear from my previous answers, is that I would like to pursue the QCD gravity connections and see where they lead us. And I find this tremendously exciting. Personally, I hope this would provide me with a window to think usefully about aspects of quantum gravity and string theory. So I'm hoping that my work coming from the QFD side of things will kind of make crisper for me what may be missing in such approaches. That's one possible path that I see developing. I enjoy thinking very much about precision science and developing new computational techniques for this. This extends to my thinking about quantum computation and some work I've done recently on it. And even though the prospects of quantum computing really revolutionizing precision science in QCD or real world theories are likely beyond my lifespan, but it's still interesting to think about because of all the conceptual issues involved. I'm also very interested in this regard in tabletop cold atom experiments and how we could possibly engineer these to provide us with insight into the many Bonnier features of gauge theories. There's some really exciting work going on in this direction, and that I would like to learn more about and hopefully contribute in some small way to.
Thank you so much for this insightful discussion. Lastly, what piece of advice would you like to give to our young audience?
So this is your hardest question. I've been very passionate about theoretical physics since I was a teenager. When I encountered the Feynman lectures in physics, and that kind of set off this ongoing passion that I pursued for I don't know, I guess about 4 years of my life. And physics to me, therefore, has always seemed like an avocation and not a profession. Even though from the outside, it might seem I pursued a fairly conventional career. One piece of advice I would give to anyone who wants to do research in theoretical physics and get involved is to continually try to step outside your comfort zone and learn new things. This is what I found early in my career, so taking intellectual risks and jumping into things that seemed exciting, even if I didn't know much about them. But I know this is easier said than done, and it's especially true as one gets older. People are more and more reluctant to get out of their comfort zone for various reasons. But it is absolutely essential to discovery, because it is precisely the opportunity to bring fresh perspectives to well-established problems in a given field that give you that little window of opportunity to say something new about problems. So that's kind of my primary advice, is to keep taking intellectual risks and not being afraid of being thought of or looking stupid, because there's that 1 in 1,000 or million chance, depending on your perspective, that you could really stumble into something really exciting and new that will give you continued motivation for a long time to come. So that's really my only observation, perhaps not a very original one.